What's up, y'all? I'm Mindful. In today's video, we're going to cover the thought experiment and Paradox's Iceberg. In this iceberg, it covers a wide range of topics dealing with more philosophy, quantum mechanics, time travel, and all that good stuff. So I hope you guys enjoy this video, and let's get right into it. So the first entry on this iceberg is the Barber Paradox, which is a paradox invented by Bertrand Russell that is dealing with a barber that states, this barber is the one who shaves all those, and those only, who do not shave themselves. This is pretty simple at face value, but then you gotta ask yourself, who shaves the barber? There's no answer to this question, as the barber cannot shave himself because he can't shave people who shave themselves. And so now if the barber doesn't shave himself, then he fits into that group of people who the barber would shave, and henceforth would be shaving himself. So there is no answer to this paradox, as this barber can never exist. Alright, so the next entry is the liar paradox, and this one's a pretty simple one. It states that if a liar were to declare the phrase, I am lying, then the liar is not lying, but instead is telling the truth. But he's also lying by doing that, which is then again telling the truth. Another example of this would be if I were to say this sentence is a lie, which technically would be the truth, but since it's a lie, then it's also false. So with this paradox, you have statements that are both true and false at the same time, so really, what are they? You're going to see a ton of this on this iceberg. Alright, so the third entry on this list is Opposite Day, and I'm sure most of y'all watching this video have played Opposite Day when you're a kid. This one isn't really a paradox at all, but it's simply just what Opposite Day is. You know, everything is opposite. So I'm not going to spend much time on it, it's pretty stupid. Alright, so the next entry on this list is the Mony Hall problem, which is based off of a game show called Let's Make a Deal and named after its host, Mony Hall. The question is phrased as this. Suppose you're on a game show and you're given the choice of 3 doors. Behind one door is a car, behind the others are goats. You pick a door, say door number 1, and the host, who knows what's behind the doors, opens another door, say door number 3, which has a goat in it. He then says to you, do you want to pick door number 2? Is it to your advantage to switch your choice? In this paradox, you may think that staying or switching doors has no effect on your probability, but instead, it actually changes your odds from 1 to 3 to 2 to 3 if you switch. This paradox is a whole rabbit hole that I can go down if y'all want me to, but there's so many solutions and explanations to this that it's too complex to put in one video. But in simple terms, when you pick the first door, you only have a 1 out of 3 chance of being right. In all 3 possibilities, there's only one of them that includes you having the car in the first door. The other 2 the cars are going to be in the other 2 doors. So, if the host reveals the goat door, then there's a 2 out of 3 chance that the car is in the door that isn't the one you picked. Again, like I said, I could explain this a whole lot better in another video if y'all want me to, but that's just it in simple terms. So, the 4th entry on this list is Xenos paradoxes, and these paradoxes are thought to have originated from Parmenides' doctrine of monism, which is the reality that all is one and nothing changes it. This is another one I could do a whole video on, as there's 9 different surviving paradoxes that have been found in this video, and I don't want it to be like 10 hours long, but I'll give you what are considered to be his 3 most famous. So the first is the dichotomy paradox, which states that which is in locomotion must arrive at the halfway mark before it reaches its destination. This seems simple at first, but this implies that an infinite number of tasks that have to be completed before one can reach its destination. You first must reach halfway, then you must reach halfway of the halfway distance, and it keeps going down into smaller values infinitely, which will never end. Another problem is that this paradox contains no distance originally, and henceforth the paradox can never start because there is no distance that is able to be cut in half. This paradox also implies that no travel can even be completed or begun, and therefore motion is an illusion. His next one is called the Achilles and the Tortoise, which states that Achilles is in a foot race with the tortoise, and he allows the tortoise to get a 100-meter lead on him. In this race, the fastest runner can never reach the slowest, since the fastest must first reach the point where the slowest started, and the slowest must always hold a lead. So, say the tortoise has a 100-meter lead on Achilles, and then Achilles reaches the 100-meter mark. The tortoise, by that point, has then moved an even smaller number, say like 2 meters, and Achilles now has to reach that point. It keeps going on and on and on and on and on, and I don't really see where the paradox is, unless the question implies that Achilles has to win the race or overtake the slowest, in which neither are possible. Or if for some reason Achilles is technically now slow enough in reaching the tortoise, so the tortoise is technically faster than Achilles, and then the paradox is that the fastest runner is actually now the slowest. Honestly, I don't really know about this one from what I've researched, but that's just kind of my take on it. Alright, so his next paradox is the arrow paradox, and bear with me on this, it's like a long phrase. But it's stated by Aristotle as stating, if everything, when it occupies an equal space, is at rest at that instant of time, and if that which is in locomotion is always occupying such a space at any moment, the flying arrow is therefore motionless at that instant of time and at the next instant of time. But if both instants of time are taken as the same instant or continuous instant of time, then it's in motion. So that was rather confusing, but in simple terms, Zeno uses this paradox to state that in order for there to be motion, an object must change the position in which it occupies. But if you pause time at any given moment during the arrow's flight, it will not move because it is occupying whatever space it is occupying at that point in time. Therefore, motion is impossible. There are other paradoxes he has, but I'm going to save those for a rainy day at this point because it's already long enough. Alright, so the next entry on this list is the Fmy Paradox, and I'm sure you guys have seen hundreds of videos on YouTube that are going to do a much better explanation than I can in this Iceberg video, but this one deals with the fact that there's been a lack of conclusive evidence about extraterrestrial life and the likelihood of its existence. So the chain of reasoning goes as follows. First, there are billions of stars in the Milky Way that are similar to our sun and have a high likelihood of having supporting planets orbiting it like Earth that should theoretically be capable of sustaining life. Some of these planets have been around much longer than Earth and henceforth should have had intelligent life much earlier than we did, which would make their species more advanced and maybe capable of interstellar travel. Therefore, Earth should have been visited long before today by an alien species, but we haven't. There's a lot of rabbit holes you can go down with this one that include ideas such as the Great Filter, which I might do a video on, but this is just the surface level of this iceberg, so I don't really want to go too in depth in it. But if you want more information on this, you can go read the Wikipedia article, and it's got plenty more than what I just told y'all. Alright, so the next entry on this list is the Grandfather Paradox, and if you know anything about time travel, then you've probably heard of this one. In this paradox, you travel back in time and kill your grandfather, but since your grandfather is now dead, you couldn't have had your parent, and so therefore you could have never been born, which means you could never go back in time and kill him, which means your parent is born, and then you are born, which means you go back in time. It's a long loophole that can continuously go on and on and on forever with no end. So this results in multiple contradictions and can have multiple different observations to it. Again, time travel is a massive loophole that you can go down, and I will go down in another video, but this is just the basic understanding you need to know if you want to theorize about time travel in the past at all. Alright, so the Ship of Thesis is a paradox that was invented a long time ago that deals with the idea of what an identity's... scratch that. So the Ship of Thesis is a paradox that was invented long ago that deals with the idea of what an object's identity is. In this example, take a ship. Every now and then, the ship takes damages on travels and parts of it have to be replaced. After hundreds of years of maintenance, every part of the ship would have been replaced at some point. Therefore, you must ask yourself, is this ship the same ship from back then, or is it a totally new ship, and at what point does it become a new ship? If you want to go a bit deeper into this, let's take into account the human body. Over your lifetime, every single cell in your body is going to be replaced by a new cell to fix those dying cells. So, using the philosophy that we just used, are you still the same person from when you died to when you're born? There's no really correct answer, it's just kind of up to you to decide that. The next entry is Schrodinger's Cat. Forgive me if I butchered that, but it's a thought experiment in which a hypothetical cat can be both dead and alive at the same time. In this, a cat is placed in an unobserved box and is linked to a random subatomic fate that may or may not occur. Let's say a 50-50 chance. In this, a flask of poison and a radioactive monitor is placed in the box with the cat. And if any radioactivity occurs, for example a particle decaying, then the flask shatters and the cat dies. This is a problem of quantum mechanics and superposition, which at some point the cat is both dead and alive if the box stays unobserved, but at some point you will open the box and the cat cannot be both dead and alive at the same time. This one also has a famous multiversal rabbit hole you can go down, which I will save for the later in this iceberg. Alright, so the birthday problem is a hypothetical problem in which it asks for how many people you can choose, and at least 2 of them share the same birthday. You may think that you have to find at least like 100 people to even have a 50% chance at that, but what if I were to tell you that you technically only need 23? This is because you have to analyze the pairs of each, and by doing the math, you have 253 pairs to consider, which is way more than half the number of days in the year. I'm not really qualified to give you like the complete math on this, but it's a lot of permutations and combinations that you have to solve to figure out, but it's interesting to think about. So the inverted spectrum is a hypothetical concept on color. This idea was created by John Locke and proposes that one day you wake up and all the colors in the world are inverted. This also deals with qualia, and in order for you to understand any of this, you have to understand that qualia refers to anything that you can classify subjectively. For example, color is a qualia because no individual sees the same two colors. But for this, it states that if the inverted spectrum were possible, then we have to admit that qualia exists because these things are non-physical and only what we perceive. If the world changes color, it only changes the way you would perceive it and not actually how you interact with it. So Catch-22 refers to the paradoxical logic that Joseph Heller uses in his 1961 novel of the same name. This refers to a situation in which one cannot escape because of its contradictory rules or limitations. The logic used in the book deals with a pilot who wishes to be grounded from combat flight on the grounds of insanity. So, in simple terms, it deals with the insanity of a pilot to continue flying. For example, it asks if you are concerned with your own safety flying these planes. If the answer is no, then you are insane but must continue flying missions anyway. If you answer yes, then that is rational and you are technically sane, so you cannot be exempted on the grounds of insanity, so you must continue flying anyway. I'm sure a lot of you have seen different flowcharts on different topics using this knowledge that regardless of what you answer, it will always lead you to the same result, but this is just the example he uses in the book. So this one was actually at the very bottom of the iceberg as a joke, but I think it's funny to mention, so I decided to put it up in the first year. So the Rick Astley paradox states that if you ever ask Rick Astley for the movie Up, he will never give it to you because he says that he's never going to give you up. But at the same time, he's going to let you down by doing so, so he has to give it to you. But he can never give you the movie Up. I just thought this one was funny to mention. There's really no deeper meaning to it. Alright, so the trolley problem is an ethical problem that deals with the human ethics and psychology of a human. The most simple version of this problem states that there's a runaway trolley running down the railway tracks. Ahead, there are 5 people tied up and unable to move, and the trolley is heading straight for them. You are standing next to a lever that, when pulled, the train will divert and save those 5 people, but instead hit one singular individual standing on the tracks. We can further this and say that that one individual is like your family member or something. Or someone close to you, so that making this decision is actually a lot harder. So, what do? Pull the lever and let it hit the person close to you, or don't pull it and save them instead and hit 5 other people? Honestly, I don't even know what I would do in this situation because there's so many moral things that you'd have to consider. But that is up to you to decide what you think because your answer is based on your own morals. So the infinite monkey theorem is one that you've probably heard of, and it's pretty relevant in pop culture, and it is a theorem that states that if a monkey were to sit in front of a computer or typewriter, then he eventually would be able to type up any given text. For example, the works of Shakespeare or even the script of this video. Even further, with enough time, he would be able to type every single possible combination of text. This one's rather simple, so I'm not going to spend much time on it. The Library of Babel is an idea written as a book in 1941 by Jorge Luis Borges. Forgive me if I said that name wrong, but that describes a library that contains every book that ever was and or could ever be written. Much like the biblical story of the Tower of Babel, this library implies an infinite number of books and an infinitely expanding building. There isn't really much to this one, but it's an interesting comparison you can make with this. The internet technically could be thought of as this imaginary Library of Babel, where eventually we will have every book ever written on it, and it is theoretically expanding every day. And another thing with this is that this library has to have every combination and permutation of every book ever written and should therefore be infinite. However, an individual by the name of W.V.O. Keene, I think that's how you say it, but he stated that the Library of Babel is actually finite because any text that doesn't fit into one book can be reconstructed by finding a second book that has the continuation. The Library of Babel could technically only contain 2 books. Using Morse code, you have 1 book with a dash and 1 book with a dot, which can make every text ever, just using those 2 characters. Alright, so the next entry on this list is a Dyson Sphere. And a Dyson Sphere is a hypothetical megastructure that surrounds a star and captures all of its energy. This was thought of to be a hypothetical solution to what happens whenever a civilization runs out or becomes advanced enough to exceed the energy output of its own planet. This hypothetical structure would produce tons of more energy than any planet could ever output, and it's pretty much key to being a tier 2 civilization. If you don't know what that is, it's a ranking on the Kardashev scale, which is a ranking of how much energy and like the tier of civilization that a species is. But I'm sure you can figure out that a structure of this capacity is far from what humanity is able to produce right now. Currently right now, I think we're about a 0.74 on the Kardashev scale. So we're not yet a tier 1 civilization, which is using all that a planet can output. It's interesting to think about if you like thinking about the future, but again, this structure is so far away right now that it's not even conceivable to what we are right now. All right, so this next entry, I'm going to preface this by saying that this is a controversial topic dealing with abortion, so I'm only going to give you the surface level on this, and I'm going to try to stay clear of controversial stuff. But this is an argument written by Judith Jarvis Thompson, if I'm getting that right, in Philosophy and Public Affairs in 1971, and goes like this. Suppose you wake up in the morning and find yourself in bed with a famous violinist. He's found to have a fatal kidney problem, and you are the only one with that blood type to match him. So, the Society of Music Lovers has captured you and plugged your circulatory system into his to extract the poisons from his kidneys. And if you unplug him right now, he will die, but in 9 months, he can be safely unplugged. I'm sure you can figure out how that all translates to, all that. And I'm not really going to mention anymore. I'm just going to move on to the next one. All right, so the next entry is the Chinese room, and this is a thought experiment that proposes of how AI will never be truly intelligent. And by intelligent, I mean that they don't have thoughts and can't truly behave like a human. All right, so quick editor's note here. I lost the rest of the footage of this, so I'm just going to do a quick explanation right here. So in this experiment, an individual that is non-Chinese speaking is given a book of Chinese translations in their native language, and a native Chinese speaker is standing outside of the door. Then the Chinese speaker will communicate with the non-Chinese person because that person is able to translate everything back and forth in order to communicate, but they don't actually know Chinese. Therefore, the person outside the room thinks that this is a Chinese person they are talking to, when in fact they don't know anything. This is used to say that artificial intelligence can convince you that you are talking to a human, but it isn't actually human because it is simply doing what it is told to do. I'm sure that was confusing, and again, this one can go down a long rabbit hole, but that was just the basics of it. Alright, so the Lottery Paradox was created by Henry E. Keiberg Jr. Forgive me if I'm saying that name wrong, and it assumes that there's a 1,000 ticket lottery that has exactly one winner. If you know that, then it is rational to assume that there's one winning ticket. Now, consider you buy a ticket. You can rationally assume that that ticket will not win because your odds are so astronomically low. Now, do that with all 1,000 tickets. It is rational to presume that every single ticket will not win. So now there's two rational answers to the lottery that create a contradiction. One is that one ticket wins, which was stated before, and one that no ticket wins, and using a principle of rationality. So, in simple terms, don't play the lottery. And with that, we finish the first tier of the iceberg, and we will move on to the next one. Alright, so Hilberts Hotel is a thought experiment introduced by David Hilbert in 1924 that imagines a hypothetical infinite hotel with rooms numbered 1, 2, 3, and so on. Before I get into this, there's a great YouTube video on this out there. I've watched it. It's gonna cover more than I can in these like 2 minutes. So if you want more information on it, then go check that out. But for this, let's assume that initially every room is occupied in this infinite hotel, but more people arrive. So how do you deal with each new guest if every room is filled in an infinite hotel? If there's a finite number of guests, you simply just have everyone move down as many rooms as the number of guests you have. So, for example, you have 4 guests coming. That means the person in room 1 would move to room 5, the person in room 2 would move to room 6, and so on. Now, if you have an infinite number of guests, then this strategy doesn't work at all because you cannot move everyone down an infinite number of rooms. Instead, what you would do is make everyone double their room number. So, for example, the guest staying in 2 would move to 4, 4 moves to 8, so on, so on. So every guest that was in the hotel before is staying in an even number room, and therefore there's an infinite number of odd numbered rooms that the new guest can accompany. So the paradox here is that there's a contradiction between the statements that must be assumed, and that is that there's a guest to every room and there's no more guests to be accommodated, both of which are false in a hotel with infinitely many rooms. So the Baktari Paradox states that suppose you have a solid ball in a 3-dimensional space that can be chopped up into a certain amount of subsets, which then can be reassembled and create 2 identical copies of that ball. Those subsets are not finite, however, but instead are an infinite scattering of points. Therefore, you can do this with an infinite number of times and have an infinite number of balls. This paradox contradicts basic geometry, and I mean, to be honest with y'all, I might be able to explain this a little bit better, but I really don't understand this one. Alright, so the next entry on the list is the twin paradox, and I'm going to keep this one simple for y'all because you can go down a whole rabbit hole of the space-time continuum, so I'm just going to give you all the basics of this one. So, say you have two twins. One of them is on Earth, and one of them is on a high-speed rocket traveling in space. I'm talking like probably moving at like light years of speed. But after 3 years, the twin on the rocket returns to the Earth and finds that their sibling has aged 2 more years than they have. This is what is known as time dilation, because since the twin on the rocket is traveling at the rocket speed and the twin on Earth is traveling at the Earth's rotational speed around the sun, the twin in space is going to experience less time than what the twin on Earth is. Using logic, there isn't really a paradox here, but again, you could go down a whole rabbit hole. So the prisoner's dilemma is a thought experiment that involves two prisoners, and if y'all have ever seen those game shows on TV that have those two people where they have a steal button and a split button, where if you hit the steal and the other person hits split, you get to take all the money, and if the other person hits, or if y'all both hit split, and then y'all both split the money, but if y'all both hit steal, y'all get nothing. That's pretty much what this is, but it's like kind of the opposite. So, you have two prisoners, and the police have admitted to them that they don't have enough to put them away, so they're going to give them each 1 year. But if one of the prisoners decides to rat on the other, then this one prisoner will get let off, and the other prisoner will get 3 years. They've both been given this option, and if they both choose to rat on each other, then they'll each get 2 years. There's no communication between either prisoner, and you can reasonably assume that both prisoners want the shortest amount of time possible. So, by using that logic, you may assume that, oh, they'll both probably choose to like stay quiet and each get 1 year. But rationally and using logic, if you are in that situation, that is not your best option. Your best option is actually to rat, because in all of the scenarios, if you rat, you're either going to get 0 or you're going to get 2 years. But if you stay quiet, then you could get 1 year or you get 3 years. So the best choice is to actually rat, and you're going to get less time either way. Alright, so Hitler's murder paradox is a throwback to what I mentioned earlier with the grandfather paradox, where in this scenario, instead of removing the ability to time travel yourself, you remove the reason to go back in time from the first place. So in this one, you're going to go back in time and kill Hitler before he can start World War II and the Holocaust. Now, since World War II has not happened because you killed Hitler, there's no reason for you to go back in time and prevent what hasn't happened. Again, this is much like the grandfather paradox, where it creates a continuous loop where you go back in time, kill Hitler, World War II never happens, you have no reason to go back in time, Hitler's still alive, World War II happens again. It's a continuous loop that is never going to break. Again, time travel has so many stipulations when it comes to traveling in the past that you start to wonder if it would ever actually change anything. Alright, so the paradox of free will is a rather interesting one because there's no really correct answer to this when you think about it. But so we as humans assume that we have free will. But when you add the concept of time to it, you technically don't. So let's say you have two choices, choice A and choice B. You should have free will to choose what you want to do, but you don't. So if you pick choice A, then there's never a timeline in which you pick choice B. So technically, choice A was your only choice. It's the same thing if you pick the opposite choice, like just, choice A would have never existed. So in the first place, did you really have the free will to pick if only one outcome was ever going to happen? This part of the paradox is rather surface level, but it can be used to prove both the existence and non-existence of God, which I find rather interesting. So the Omnipotence Paradox is a paradox that comes with the concept of the word omnipotence. This isn't just a paradox, but has a ton of different subsets, and much like the previous one, or the previous entry, this one can be used in debating the existence of God. But being omnipotent assumes that one is able to do anything. So, can an omnipotent being create a stone so heavy that it itself cannot lift? If so, then it is not omnipotent because it cannot do everything because it can't lift a stone. But if it can't create that, then it's not omnipotent because it can't create that stone. Basically, the entire family of these paradoxes fall under this requirement of the omnipotent being to break the rules of logic. And we don't even know if omnipotent beings are bound by the rule of logic. So, alright, so this paradox is actually just kind of stupid. It's called the interesting number paradox. And this paradox states that every number is interesting in some sort of way. And you may think right now that you could come up with a few numbers that are uninteresting, and let's say you come up with a group of 5. Well, technically the smallest number is interesting because it is the smallest uninteresting number. It makes sense, but this one's just kind of stupid. Alright, so this next one is the repeating 9 paradox, which is one that you've probably heard from every single math teacher you've ever had. 9 repeating is a number where it is a repeating number of 9s after the decimal and as close to reaching 1 as hypothetically possible. The problem comes when 3 is brought into the equation because 1 divided by 3 is 1/3, which in decimal form is 0.3 repeating. If you add another third to that, you get 2/3 or 0.6 repeating. Now, if you add another third, you get 3/3 or 0.9 repeating, but 3/3 is technically equal to 1. So 1 equals 0.9 repeating, but then technically no, it doesn't because 0.9 repeating is not 1. So there's been a ton of calculations on this that are so advanced that I can't explain them to you. And I don't think mathematicians still don't have an answer to this. All right, so Gray's paradox was a proposed paradox that tried to conclude that dolphins should not be able to move the way that they do in water because of their physiology and the drag forces of water. However, this theory was debunked as an experiment was done that proved that dolphins' tails were much more powerful than the original creator of the paradox had originally proposed. So this one's been debunked. All right, so the Grim Reaper paradox, this one's a variation of one of Xenos paradoxes I mentioned earlier, and it's dealing with the logical consequences of an infinite chain of events. So for this one, assume that a person is alive at midnight. A Grim Reaper is tasked to kill that person at 1 a.m. But there's a second Grim Reaper who is tasked to kill him at 12:45. But there's a third Grim Reaper who's tasked to kill him at 12:30. This goes on until this literally is an infinite chain of events at where one Grim Reaper is going to be tasked to kill the person earlier than the Grim Reaper before it. So in theory, the person should never be alive at midnight because there's always going to be a Grim Reaper that would kill him before that time. But the paradox states that they are alive at midnight, and this could be taken back days, weeks, months, years, even the beginning of time. So the person is both alive and dead at midnight. Alright, so the double split experiment, this one, bear with me, this was another quantum mechanics and physics one that I don't really understand, so just hold on. In this experiment, you have particles that you shoot through 2 closely spaced slits. When using one slit, the particles would behave like bullets, but when 2 slits are used, the particles start to exhibit wave-like patterns, interfering with each other. Another part of this is that whenever the particles are not observed, they exhibit wave-like behavior, but when observed, you cannot see the wave patterns and they behave like individual particles. That was my best job at explaining this one. If you know more, I'd love to hear your answer to this, because like I said, I don't have a degree in quantum mechanics, so I'm just going to move on. The next entry is Kafka's Toxin puzzle. And in this one is a thought experiment that goes as follows. A billionaire places you in a room with a vial full of toxin that if you drink will be painful for like a day, but it will not kill you or have any lasting effects. He will give you $1 million if by tonight at midnight you intend to drink the poison tomorrow afternoon. You do not have to drink the poison to get the money, but you do have to intend to do it in order to get that. So can you intend to drink the poison if you intend to change your mind later? The proposed solution to this revolves around 2 statements. One is that since this is a reasonable reward, you have reasonable grounds to intend to drink the poison, and the other states that there is no reasonable grounds for the person to actually drink the poison since there is no reward for doing so. Then you could never even want to intend to do it in the first place. So you can never intend to do it. Newton's Cannonball is a thought experiment by Isaac Newton that is used to basically state that gravity is universal. In this scenario, there's a rock or projectile on a high place with little or no air or resisting qualities around it. When you throw that projectile, it would do one of a few things. If it has low speed, gravity brings it back down to Earth. If it has moving at orbital speed, which is the speed at which the Earth moves, then it will rotate around the Earth back to the exact spot at which you threw it. If it is higher than that, but the speed is not high enough to leave Earth, then it will rotate around in an elliptical orbit. And if it is high enough to leave Earth, then it would travel in a parabolic trajectory outside of Earth. Basically, this one is just an explanation of gravity in a scientific thought experiment way. Alright, so the Turing test, this one is very similar to the Chinese room in that it deals with the capabilities of a computer or AI to behave like humans. In this instance, you have a text chat between a computer designed to imitate human responses and an actual human, and someone sitting outside who is seeing both the text chats and trying to determine which one he thinks is human or not. If the person outside cannot reasonably decide which they think the computer is, then the computer has passed the Turing test. This one doesn't necessarily imply that AI would be able to mimic human consciousness, but it does imply that it can mimic human-like behavior. And with that, we've concluded Tier 2 and the final part of this video. I plan to release this video in 3 parts, as there's 6 layers of the iceberg, you have 2 tiers for each video, and I'll put them all together at the end if you want to watch them all at the same time. But like I said, this video took a lot of effort and a lot of time to research, so if you liked and subscribed, it would mean a lot to me. Also, I just wanted to throw my, face in here because it's just easier for me to record and, all that. So if you like the stock footage from like the 2 videos before, then I'll gladly go back to that if y'all want. Or if you want me to record like gameplay of a game and I'll post that at the background, like I'm cool with that too. So anyways, I'm mindful and I hope to see y'all in the next part.